So examples, let's start with something very simple. Let's just take R2 with one of those P norms that we've been looking at, and let's see whether or not we can find a compatible scalar product in the sense of our formula star. So by our corollary, we have to check the parallelogram identity, and of course that has to hold for all x and y in the space. Of course we cannot check it for all, so let's just check it for two easy ones. It's not a good idea to take 0, 0 as one of the two vectors, because then you will always be happy. Well, maybe let's replace one of the zeros by 1. Let's take this as the first vector, and then just to be fair, second vector like that, and see what happens. So let me squeeze this a little bit so the parallelogram identity is still visible. Okay, so we need to check whether the sum of x plus y, which is 1, 1, its norm squared together with the norm squared of x minus y, which must be this, is the same question mark as 2 times just the norm of x squared and 2 times just the norm of y squared. Okay, our norm is the P norm, as you remember. Now I think I can scroll away here. So this here is just the pth root of 1 squared, 1 to the power p plus 1 to the power p, and then there's a square outside. And here's the same pth root 1 to the power p and, well, modulus minus 1, which is again 1 to the power p squared. And the question is still whether or not that is 2 times pth root 1 to the power p plus 0 power p squared and 2 times pth root 0 power p plus 1 power p squared. Okay, I think we can hugely simplify matters here. So underneath the root there is 1, whatever your p is. So this is pth root of 1 squared is again 1, so we could just say this is a 2 and this is another 2. What do we have here? Well, this is always 1, so this is always 2. Same here. So what do we see? We see 2 to the power of 2 over p plus, and here the same, 2 to the power of 2 over p, and the question is that the same as 2 plus 2? Well, here's the exponent here is 1, the exponent here is 1. So the question is whether or not 2 over p is the same as 1, or to phrase it differently, whether or not p equals 2, and that's your condition. So you can see that these two vectors here give you equality in the parallelogram identity if and only if you're using the 2 norm, not for any other p. On the other hand, we know that for the 2 norm we have a scalar product, and that's why the parallelogram identity must be true for any other vectors x and y also. So what did we just learn? We learned that this is this has a compatible scalar product if and only if p is 2. Or we could say, let's say that here, so R2 with the p norm is a Euclidean space, and hence the Hilbert space because it is complete. If and only if you're taking the 2 norm, if you're taking p equal to 2. Okay, and that example is already showing you the way to the other examples, which we can put very short. So our second example could of course be r to the n with the p norm, and you would do the very same computations. You could probably take x equal to 1, 0, and all the rest zeros, and y equal to 0, 1, and then the rest zeros, and you would end up with the same conclusion. And the same also works if you take infinitely long vectors. So you could also look at LP with, of course, the P norm. Otherwise, it's not a norm space. Same proof, same conclusion. And we can carry on even further. You could take, as a fourth example, capital LP functions on some interval AB and equip them with a P norm. And you have the same, let me just copy this, same proof, same conclusion. So this time you could take x as a function which over the interval from A to B is 1 first and 0 then, and as a function y you would take one that is first 0 and then 1, and then it might or might not go back to 0. A somewhat more interesting example is number 5, the continuous functions. So remember our set of continuous functions over an interval from A to B. We can try to equip that again with the P norm for functions, which is, an integral norm over the p powers of the data, and then ask whether or not this would give you a scalar product. And we kind of know the answer. You can do the same tests as before, only you would now use continuous functions, so you shall not let them jump here, but you make the transition from 0 to 1 a bit smoother, and then end up with the same conclusion. So you would see that this is Euclidean, so it has a scalar product if and only if you take p equal to 2. But on the other hand, last time we saw that it is complete. That was in the Banach space section, if and only if you take the infinity norm. Well, that's quite a twist. So we never get it a Hilbert space, because if it's Euclidean, then it's not complete. If it's complete, then it's not Euclidean. For a Hilbert space, you would need both of them. So never a Hilbert space. There is, however, a trick that one can apply to turn this into a Hilbert space, but then it's not itself anymore. The trick is to look at the so-called completion. Well, this is not something that we can cover in this course. I'm just saying it for completeness. Yeah, completeness in every sense you can think of. So take the completion, and this is not something that we did explain, but if you know what it is, then you can understand that sentence, and if not, then no need to worry. take the completion of CAB with the 2 norm. So we want the scalar product and we want to make it complete because it's not. Then you get the Hilbert space because then it's complete and still Euclidean. And well, you'll be or be not surprised. The result is going to be just what we call L2 AB with the 2 norm. So in order to make it complete with such a weak norm, you need to include so many new and discontinuous functions that you do not recognize the space anymore.